Hello, this is Todd Frazee and this is ADVM 12, Unit 7. It's the second half of Chapter 6, page 217. So we're going over more datum references, specifically in the feature control frames now, and advanced applications of them. So a little more examples of applications of the principles of this chapter. Introduction. This unit will focus on advanced applications of datum references, including how a datum reference frame can be simulated using three mutually perpendicular surfaces. You can learn how to apply material boundary modifiers to datum feature references and understand their impact on manufacturing and inspection. Additionally, you will explore how datum features constrain specific degrees of freedom in a datum reference frame. This unit will also cover the use of movable datum target symbols and the application of translation symbols to datum features references. By mastering these advanced concepts, you will be able to apply GD&T principles more effectively in more complex engineering designs. Okay, the objectives. Explain how a datum reference frame may be simulated when three mutual perpendicular surfaces are identified and referenced as datum features. Use material boundary modifiers on the datum feature references and explain the significance of the modifiers. We're going to identify the degrees of freedom constrained by each reference datum feature in a datum reference frame, and explain the requirements of a translation symbol applied to a datum feature reference. Okay, order of precedence. We touched on this in the last unit, but any tolerance specification that changes order of precedence for the datum feature references results in a different datum reference frame. So take care when selecting the correct datum features and the reference order. Determined by design function and manufacturing considerations. The part edge faces identified as secondary and tertiary datums. So typically your datum A is going to be a flat plane, is your primary, and then the other two are going to be associated with edges that are somehow 90 degrees to that first plane. So if it's labeled A, B, C, that would be the order. But if you had other combinations, they show what, 1, 2, 3, 4, 5, 6 combinations, they actually result in different constraints, especially if for the primary one. Okay, the number of datum feature references specified by the tolerance characteristics affects the required number. The tolerance characteristics and intended level of control determine the degrees of freedom needed to be constrained by the datum feature references. The types of datum features also affect the number, and types of datum features and order of precedence affect what degrees of freedom are constrained. Okay, there are three mutual perpendicular flat datum features. Reference three datum features if features are flat and a three-plane datum reference frame desired to contain all 6 degrees of freedom. The three planes are infinite in size and not limited by the size of datum features or simulators. So it's kind of like in your CAD software, the planes go off to infinity. Okay. And coordinate system origin for tolerances referencing all three datum features at the intersection of the datum plane. So when we're constraining a model, or constraining them in several planes. Your primary plane would typically be the one you select your initial sketch on, and you have your origin that would where all three planes come together. Okay, there's one cylinder and one flat datum feature. It's not always necessary to reference three datums features to establish an origin and three axis coordinate system when you have a cylinder and a flat. Okay, the flat primary datum feature establishes one plane that contains two axes and sets the direction of one axis. The secondary cylindrical feature establishes an axis that locates the origin on that plane. Rotation not constrained around one axis, and do not always need to restrain all 6 degrees of freedom depending on the part. Okay, one surface and two features of size datum features. So one surface and two features of size may be referenced as datum features. So your primary and secondary can constrain 5 degrees of freedom, and the tertiary datum constrains the remaining rotational degree of freedom. So in our example over here, we have a primary datum of A, and it's the back side of this part. And the secondary is B, which is going to be the actual diameter of a hole. And then C is going to constrain the object parallel to the sides of the slot. And I believe it's going to imply that it is centered on the width, that the when it replaces the dimension arrow line on a linear dimension that spans a center line, as shown. Okay, datum feature references RMB, MMB, and LMB. So just for review, that's regardless of material boundary, maximum material boundary, and least material boundary, which affects the material condition. It's the material size of where the datums are actually called. Okay, so AME, or actual mating envelope, makes contact with the datum feature for RMB. The process is to establish an extent of contact and the extent of contact varies. Depends on the geometry of the datum feature, order, and precedence, and the tolerances applied to the feature. Datum feature simulator has fixed size if modified with MMB or LMB. And the simulator and datum feature not required to make contact. Order of precedence and applicable tolerances impact the size and the orientation or location requirements for the simulator. A datum feature references MMB. So a feature size may have more than one material boundary when more than one tolerance is applied. Maximum material size, only the size limit that includes the most material, and multiple possible boundaries if size tolerance and geometric tolerance applied to the datum. Only one is correct for the specified datum reference. Primary datum feature reference MMB, size only. MMC for a feature, also the MMB only when a size tolerance is applied to the feature. Okay, primary datum feature reference MMB, size and form tolerance. MMC and form tolerance combined and create MMB when straightness tolerance is applied to define an allowable variation derived from the median line is included. A secondary datum feature reference MMB, size and orientation tolerance. MMC and orientation tolerance combine to create MMB. When orientation tolerance applied to a secondary datum, feature of size is included. The tertiary datum feature reference MMB, size and position tolerance, is applicable maximum material boundary determined using tolerance applied relative to the higher order precedence datum features. It may not include size, form, orientation, and positional tolerance effects when it's associated with the tertiary datum. The tertiary datum feature reference MMB for translation modifier. The translation symbol on the tertiary datum feature reference releases constraints on the translational degree of freedom for the tertiary datum feature simulator, so it allows it to have some movement. And it's applicable at MMB determined using remaining tolerances that constrain the datum feature to a higher order precedence datum, so it allows that datum to move a little bit more, allowing the primary and secondary to have precedence. Translation modifier is added to the datum feature C reference on the previous slide, and MMB equals MMC plus orientation tolerance and simulator free to translate. Okay, so datum feature reference LMB. Regular feature of size at LMC if the size limit or tolerance boundary contains least amount of material. And LMC is equal to the least material size, or LMS, and no perfect form boundary if no tolerance is applied. Perfect form boundary is required at LMC if LMB modifier is shown. Two profile boundaries created if irregular feature of size or surface has profile tolerance applied, and least material boundary, the profile boundary containing the least amount of material on the part. And avoid datum feature references with LMB modifier unless essential to meet the design requirements. Further considerations of modifiers on datum feature references is MMB increases the allowable variation and can reduce detail part costs. When I say detail part, it's an individual part, not an assembly. It may adversely affect the function due to the additional allowable variation. LMB also allows additional variation. Wall thickness protected, but worst condition wall thickness permitted to occur at all sizes of reference datum features. So you got to be careful when you're doing thin wall designs. And RMB eliminates any additional tolerance based on the boundary departure, and it reduces variation but can also increase cost.